Let's do some examples. So here I have an indefinite integral, x squared plus 1 cubed, 2x, and I want to find all antiderivatives. So we're going to do that. I'm going to use the method of substitution. I'm going to identify u, change variables, find antiderivatives, and change variables back. So let's look at the identifying u part. So that means I want to look for an inside function for a composition. So one composition I notice is x squared plus 1 first inside the parentheses, and then raising it to the third power. So that's a composition. In fact, whenever you see parentheses, you should see that as a telltale sign for having a composition. The inside is what's inside the parentheses. So here, I'm going to set my u, that's identifying u. Now, what I want to do also is find a du. That is, I want to find something that looks like u prime of x dx. And here's dx. And in fact, du, if u is equal to x squared plus 1, then du is 2x, that's the derivative of x squared, times dx. Okay? So in fact, this is du. It's set up very nicely for me. So the derivative of u is 2x. That's what appears here. So that means I can substitute everything involving x in terms of u. The x squared plus 1 becomes u. It's cubed because of this 3. The 2x dx becomes du, and the integral sign stays the same. Okay, so that's change of variables. Now I want to find the antiderivative. So the antiderivative u cubed by the anti-power rule, if you like, is u cubed plus 1 divided by the new exponent, 3 plus 1, plus an arbitrary constant, because I'm finding all antiderivatives. That can be simplified as u to the 4th divided by 4 plus a constant. So I found the antiderivative. Now I don't have an indefinite integral sign anymore. I just have a function. But I need to change back into the variables x. So what was u? U was x squared plus 1. So I substitute back x squared plus 1 every time I see a u. Here I only see it once, so it's x squared plus 1 to the 4th divided by 4 plus c. And that's my answer. And you can check that if you took the derivative of this, you would end up with this. Okay, that's a check on the fact that this is an antiderivative for the original function. Let's do another example. Here I have an integral of x squared, x cubed plus 1 to the 7th. The telltale sign for u is the fact that I have parentheses. That's the inside function u. So I'm setting u equals x cubed plus 1. Du will be 3x squared dx. So I want to substitute for u, and I'll get u to the 7th. Now, I have to take care of these things too. I have to change them out into things involving u. And fortunately, the x squared and the dx can be paired up to give me x squared dx. And so that's part of du. What I'm missing is a 3 here. So I'm missing a 3. And the way to accomplish getting a 3 there is to multiply by 1, which is multiply by 3 over 3. That doesn't change anything, right? 3 over 3 is 1. But I can slip so this is 3 times 1/3, and I can slip the 1/3 outside. I can write 1/3. So I'll get 1/3 on the outside, integral, and now the 3x squared by multiplication is commutative can be put over there. So the 3x squared can be over here, and voila, I have du. So there's du. So 3x squared, that's du. The u to the 7th was u to the 7th, and so that integral is the same as this one. Okay, so now that was changing my variables from x to u. Now I go to finding the antiderivative. The antiderivative of u to the 7th by the inverse power rules, u to the 7 plus 1 divided by 7 plus 1. I still have a 1/3, I don't want to forget that, times, plus, c, our arbitrary constant. Okay, so that's good so far. And now what I need to do is simplify. Well, I'll have u to the 8th divided by 8. But I also want to change back into my original variables. U was x cubed plus 1, so I'll have x cubed plus 1. And instead of 7 plus 1, I'll write 8. And then on the bottom, I'll have 8, and then I'll have a 1/3 plus a constant. In fact, I can multiply the 3 and the 8 together, and I can get x cubed plus 1 to the 8th divided by 24. 3 times 8 is 24 plus a constant. So that's the answer in this case. Okay, so now I want to go to one last example of this type. Here it is, x to the 5th plus 2 squared. Okay, so what I should try to do is look for u is going to be x to the 5th plus 2. du, well, the derivative of x to the 5th is 5x to the 4th. The derivative of 2 is 0. So du is this dx. Okay, so now I do my substitution part, my change of variables. I change the x's into u's. X to the 5th plus 2, that's the same as u. So I change that to u squared. And now I still have to find a place to put dx. Well, here's dx over here. The only expression I know in terms of dx is basically du divided by 5x to the 4th. Okay? Now, if I had a 5x to the 4th here, I'd be in business. But unfortunately, there's no such thing. I don't see a 5x to the 4th here. And so I'm kind of stuck. What am I going to put here? I just can't write du here, because in order to write du here, I have to have that 5x to the 4th with me. I could write this, dx is the same as 5x to the 4th, but that's not good because I have to have everything in terms of u here. Okay, so we're stuck. So in fact, we don't want to use substitution at all in this problem. So there are some integrals like this that we don't want to use substitution. In fact, what we can do instead for this kind of problem is we're going to multiply this out. So this is the same as x to the 5th squared plus 2 times x to the 5th times 2. I'm just multiplying everything out, plus 2 squared, or the same as x to the 10th plus 4x to the 5th plus 4. And then I can anti-differentiate this. This will be x to the 11th divided by 11 plus 4 times x to the 6th divided by 6 plus 4x plus an arbitrary constant c. So here's a situation where you don't use substitution, just multiply everything out.